This week in lab, we'll be doing the modified Dumas method for molar mass determination. The purpose of this lab is to determine the molar mass of a volatile liquid. Here, volatile means that these liquids can evaporate very easily at room temperature. So they have really low boiling points, and so they'll start to evaporate without any heat added to them. So first we're going to learn about the ideal gas law. The equation for this is PV equals nRT. And P corresponds to the pressure, and the units for this are in atmosphere, or ATM, you might see it often. The volume is V, and that is in units of liters. N corresponds to the number of moles of the substance. R is a constant, which is the ideal gas constant, and that is the same number no matter what circumstance you're using. So this is always 0.08206, and those are the units for the ideal gas constant. And T corresponds to the temperature in Kelvin. So that's what that K means in the ideal gas constant. So every time you record a temperature, you have to use it in Kelvin in this equation. So our methodology, what we're going to achieve in this lab, first we're going to determine the number of moles of a substance in a gaseous sample. So to do this, we can rearrange the ideal gas equation, and we can take that N by itself, which corresponds to the number of moles. So that will equal the pressure times the volume divided by the ideal gas constant times the temperature. So we can easily measure the pressure, volume, and temperature for the sample of gas, and then we have the ideal gas constant, which is always the same. From there we can determine the mass of the sample. Then we can use that to calculate the molar mass. So remember, molar mass is grams divided by moles. So we've got our mass in grams and we got our moles, so we can find the molar mass. Then we'll be able to calculate an empirical formula from percent composition, which I'll explain later. And then we can compare that empirical formula mass to eventually find our molar mass of our substance. So the procedure, we're going to have a setup like you see there on the right, with an Erlenmeyer flask, aluminum foil, and a hot water bath. We're going to add some of the unknown liquid to the flask and be really careful to completely cover the reagent bottle when we're done with it, because these liquids are volatile, they can evaporate very easily. And so when we put it in the hot water bath, it's going to just completely vaporize the liquid, and we're going to add some iodine in the solution just so we can see when everything has evaporated. And we're going to be really careful to pay attention to when it has evaporated because we don't want to overheat the sample. Then we're going to, once we've evaporated all the liquid, we're going to condense the vapor by putting the flask in an ice bath. So it'll turn back to liquid, and we'll weigh the whole setup so that we can figure out how much evaporated. Then we can record the pressure, temperature, and volume. So the pressure will be just the pressure of the room, which we will record on the board. The temperature is going to be the temperature of the water bath, and the volume is going to correspond to the volume of the entire flask. You'll see in the video we're going to measure the exact volume of this flask. So even though it says 125 milliliters, that usually just corresponds to the top of the measurements that are written on there. It doesn't go into the neck volume. So there could be an extra 10 or so milliliters that make up the entire flask itself, so we're going to measure that. So our calculations, there are a lot of steps, so be sure to go through this PowerPoint again when you're doing your calculations for the report sheet. And just to preface, these are not your values. This is just an example, so do not use these values when you're calculating your answers. So first, for the empirical formula, you're going to use the percentage of each element, and you can assume 100 grams. So when you have the percent of each element, you just turn that percentage into grams, and then divide by the molar mass of each element to find how many moles of each element are in your substance. So we have 49% of carbon in the sample for this example, so that can correspond to 49 grams. We're dividing that by the molar mass, and we get about 4 moles of carbon. So the number of moles corresponds to the subscript in the formula. So you can see we calculated 4 moles of carbon, so that is a C4 in the formula. Same with hydrogen, we had 3 moles, and chloride, we had 1 mole. So that's how you write your empirical formula. So empirical formula is just the lowest number ratio between all the elements. Then you can find the empirical formula mass by multiplying the amount of each element by its molar mass and adding all of those together. So we had 4 moles of our carbon, so we're going to multiply that times the molar mass of carbon and get our molar mass of our entire carbon that makes up the whole formula, and then we can do the same with hydrogen and same with chloride. Moving on, we can then find the moles of the gas in our sample after we've heated it by rearranging the gas equation like I showed previously. So we're going to make sure to pay attention to the units here with all of our variables. So to turn the pressure to 8 atmospheres, sometimes it can come in the form of the mmHg unit, and so you want to convert that to ATM. We'll probably give it in atmospheres in the video just to be simple, but just in case, for your knowledge, this is how you would convert it to atmospheres. You just divide by that 760, that's the conversion factor, and you can get your pressure. The temperature in Kelvin, you start with the temperature in Celsius, which we will give the temperature in Celsius because that's our thermometer unit. And all you have to do is add 273.15 to your temperature, and you get the temperature in Kelvin. And sure you know by now, but to turn the volume into liters, you divide by 1,000 because that's your conversion factor from milliliters to liters. And then you can plug all of these into the equation and you get your number of moles. After we do that, we can find the mass of the gas and then the molar mass. So finding the mass of the gas that we've condensated, you can subtract the initial mass from the final mass. So this is the flask with the aluminum foil on it. That's going to be included in our mass. And then you just subtract them, final minus initial, and you can get the mass of the gas. Then you can use that mass and divide it by the moles you calculated in number 3, and you'll get your molar mass. So in this example, we've calculated 140.5 as our molar mass. And just pay special attention to the significant figures in these calculations. Next, we'll find the molar mass and empirical formula mass ratio. So if you remember, we found our molar mass in the previous slide, and we found our empirical formula mass a couple slides ago. So go back if you don't remember those calculations. But basically we want to figure out the ratio between the molar mass and empirical formula mass. So divide those two, make sure molar mass is on top, and you'll get some decimal ratio. You can round that to the nearest whole number. And then all you have to do is to find the molecular formula of your specific gas, you can multiply that ratio by those subscripts in the empirical formula. So we have our empirical formula that we figured out a couple slides ago, and our ratio was 2 that we calculated. So I'm multiplying each subscript by 2. So now instead of 4 carbons, we now have 8. Instead of 3 hydrogens, we have 6. And chlorides, we have 2. So that is the true molecular formula of our unknown. So that is all the calculations for this. It's only about 6 or so steps, but if you do them in this order, then you'll be good. And you can end up figuring out what exactly the formula is of the unknown gas.